And we have another quick screen cam from Seminar 5. What we're looking at here is a small signal equivalent model for this feedback bias circuit. Now inside this design we have a slight complexity in the fact that the collector loads the base with its value of current. So that means in effect that we've got some sort of feedback. So let's draw out the small signal equivalent model for this design and let's see what we get. We start off, of course, with our basic transistor, which looks like this. Our collector load resistance is connected to the supply, which effectively looks like a short circuit to ground. So here we have RC. Down here our current flow again will be IB beta, and IB is flowing into RBE. The question that we have to ask ourselves now, here is our input and here is our output signal. The obvious question is, where is RB? Well, it's connected between the collector and the base. So if I draw that on here, it connects there. Now when you try and do any of your equations, if you look in from the input, we've got a problem because we've got this component feeding back from the output. When we try and do our Kirchhoff's voltage loop around here, and we think about what's happening in this case, you think, well, is there current from the output feeding back to the input? So we've got a bit of complexity. We don't quite know what to do with this one. Well, luckily we have a theorem that will actually help us with this, and this is called Miller theorem. Miller theorem, basically derived from something called two-port network theory, allows us to take this parallel component, or this component here, in series, and convert it into two components on each side. So let's have a look at Miller theorem. Here's Miller theorem. It basically says that a voltage at one node and a voltage at another node through a resistance can be represented as a different circuit. We can move to this circuit. So here we will still maintain V1 through this resistance if the following is true. Number one, our resistor R1 is equal to R, the original resistance, divided by K over 1. K being, in this case, V in, and that being V out. Okay? So if we divide, K is V in over V out, we've got basically 1 over gain. So here we have reciprocal gain minus 1. And then R2 is this gain factor over K minus 1. So let's think about what that would look like in our small signal equivalent model and see if it will help us. So here's our transistor. I'm not putting all the labels on this time. RBE, IB, beta, current flowing that way. So we've now got a resistance here, let's call that R1, and we've got a resistance here, let's call that R2, and then we've also got RC. Okay, so if we now look at our input signal to our design, V in, this component R1, this Millard component, effectively has no input when you look in to our V in signal. It still will affect IB into the RBE resistor. What will happen in reality, some of the voltage of V in will cause a current in R1. So that infers that there will be a small current flow into the design. Let's have a look at the output stage. The output stage, we now have two components, two resistors, effectively in parallel. So R2 is effectively in parallel with RC. And our current flow will flow into that parallel combination. Okay. Well, let's just take a look at this equation for one moment. We have R2 is equal to R 1 over AV divided by 1 over AV minus 1. If the gain is high of our amplifier, 1 over AV will be small. 1 over AV will be small minus 1 will now be almost dominated by the 1. You divide through, we're basically going to say that these two components are going to approximate to being the same value. So, let's go back to our circuit, let's go back to our small signal equivalent model, and let's work it through. Okay, so let's draw out the small signal equivalent model. Here's our transistor. Here's our standard output in RC. And here's this new component, and we're just going to call it RB as a first approximation. We have RBE coming in and IB. Our output current is IB beta, and our output voltage here is V out, and we have V in. So let's write out our expressions. V out is equal to IB beta RB in parallel with RC, and I'll put them in brackets to denote them. We can write V in is equal to IB RBE. Okay, I'm just going to simplify that straight away. IB 1 plus beta RE. Now we can write out AV. AV is actually V out over V in. So if I write these two together, IB beta RB in parallel with RC, all divided by IB 1 plus beta RE. Cancel the IBs, cancel beta and beta plus 1. We are left with RB is effectively in parallel with RC over RE. That's our value for AV. Okay. Now, one thing we could probably make a note of is that RB is significantly greater than RC, therefore you could approximate it to simply RC, okay, over RE. Again, we should have a minus term in the top here because our output signal is out of phase with our input. There we go. There's another little bit of a quick